Over 13 billion years of the evolution of the universe have brought you to this point. How does that make you feel? So far in this course, we have considered how objects will move. We thought about cars driving down the road, we thought about rocks thrown through the air, but in both of those scenarios, those are just single objects moving. We did not consider what if there is more than one object and what if multiple objects are actually interacting with each other. Well, we could say multiple objects interact through forces, but then that begs the question, what is a force? If we were to say a force is an interaction between two or more objects, then we would be caught in circular logic, so we want a better definition of what is force. Now, in the previous chapters, we have learned how to describe an object's motion. In other words, if you are given position or velocity or acceleration or some combination of those terms, you know how to determine what an object's location and velocity are at any moment in time in the past or in the future. But this is describing how an object moves. This is not describing why an object moves in the first place. So what if there is an object and you want to get it to begin accelerating? If I have a coffee mug in front of me, how would I get that coffee mug to accelerate? Why does the mug accelerate? Well, if I want to get something to accelerate, I have to give it a push. So colloquially, I will say that a force could be thought of as a push or a pull. Over the next couple slides, we are going to conduct a thought experiment where we say, let's suppose we have an object in front of us and let's push on it. How do I expect that object to accelerate as a result of the push? Now, some of the things I'm going to point out are very expected. They are what we see in everyday life. But I want to say none of the questions I'm going to offer here are trick questions. I just want to explicitly point something out. And then at the end of these couple slides, we will have a way we could relate force to acceleration. So let's suppose I have an object and I give it a push. Well, I expect if I push on that object really strongly, that object should accelerate a lot. And if I give that object a push, but my push is kind of weak, that object will accelerate, but it really won't accelerate that much. So I expect that the amount of acceleration should increase with the strength of my push. Also, I expect that an object should accelerate in the same direction as my push. This is one of those examples where I said, I'm not trying to give you any trick question. I'm just pointing some things out that come from everyday experience. If I think I have a coffee mug in front of me and I push the coffee mug to the left with a really strong push, that coffee mug will accelerate to the left and it will accelerate a lot because I give it a strong push. Now, a strong push to the left is different from a strong push to the right. Accelerating to the left if I push to the left, accelerating to the right if I push to the right. The direction you push matters, and this suggests that force is a vector quantity. You not only have the strength of the push, but you also want to think about what direction you're pushing in, left or right, north or south, positive x direction versus negative x direction. You could also ask, what if you have two people pushing on an object? Well, if you have two people pushing on an object, then you have to ask, what direction are these two people pushing in? If you think about a car that is broken down on the road, if the two people are both pushing in the same direction, that car will accelerate by some amount, and that car will accelerate more as a result of two people pushing as opposed to just one person pushing. So the second person will help accelerate the car more than just what the one person could accomplish. Now, on the other hand, what if two people push on an object, but those two people are pushing in opposite directions? So one person pushes to the left, the other person pushes to the right. Well, I expect that if both of these people push with the same strength, then their pushes will tend to cancel. But if one person pushes a little bit harder than the other person, the pushes will almost cancel out, but the person that's pushing a little bit harder will win out. Or you could think of these last 2 points I made in terms of tug of war. If two people are tugging on a rope and they both pull with the same strength, nothing is going to happen. The 2 pulls on the rope will cancel. But if one person pulls in a direction a little bit more strongly than the other person, then that other person, the rope will begin to move towards the person that is pulling a little bit more strongly. The 2 pulls will almost cancel out, but not quite. So to this point, we said that it is possible for there to be multiple forces acting on a single object. But if you think back to the rocket dog example from the end of chapter 3, we argued there that a single object cannot have more than one acceleration at any given instant. This is because if it is possible to have different accelerations at the same time, then you would be able to have different velocities at the same time, and then you would be able to be in different positions at the same time, and we don't want something like that for this course. So even though it is possible for multiple people to be pushing on an object simultaneously, an object can only have one acceleration at any given moment in time. Now, this is not to say an object cannot have an acceleration that has different components at the same time. For example, it is possible to have ax be one value and ay to be a different value, but you cannot have the components of an acceleration. For example, you cannot have ax be 4 and ax be -2 simultaneously. Therefore, we expect that if we only have one force acting on an object, I expect the force to be proportional to the acceleration. If the strength of the push is large, then the acceleration should be large. But if I have multiple forces acting on an object simultaneously, the vector sum of those forces should be proportional to the acceleration. Now, I am intentionally saying vector sum here because force is a vector. We have to add it like a vector where direction is important. 2 people pushing an object to the north will give that object a pretty good acceleration. But if one person is pushing to the north and the other person is pushing to the south, the strength of those people's push is going to more cancel out because they're pushing in opposite directions. And therefore, we have to add forces as vectors rather than just add them as numbers to find the acceleration. So what are we going to ask next? Well, we said force is proportional to acceleration. A stronger force will imply a stronger acceleration. But by how much? Are there any other factors that affects the amount of acceleration of an object? How is a force on an object actually related to the object's acceleration? From experience, we also know that big objects are more difficult to accelerate than small objects. So let's consider we have a cart that is filled with gold. Now, I know gold is really, really heavy, and I know that if I give a pretty strong push to that cart of gold, the cart of gold will accelerate, but the cart of gold will not accelerate very much because it is really heavy. Acceleration is the rate of change of velocity with respect to time. I could give that cart of gold a push over some time interval, and at the end of that time interval, the cart of gold will be moving because I'm pushing on it, but it won't be moving very fast. The acceleration will be small. Delta V over delta T will be a small quantity. Let's consider the scenario where instead of a cart full of gold, I have a cart full of feathers. Now, if I have a cart full of feathers, the feathers are much lighter than the gold. So I give the cart of feathers the exact same push for the time interval that I gave the cart full of gold. But because the cart full of feathers is much lighter than the cart of gold, I expect that cart full of feathers to accelerate a lot more. At the end of that time interval, the cart full of feathers will have a much larger velocity than the cart of gold. So from experience, we know that moving big objects is more difficult than moving small objects. So what we're going to claim is if I only have one force, if there is only one person pushing on an object, The amount of force is related to the acceleration by F equals ma, where both force and acceleration are vector quantities. So remember that when you have a vector, you have to consider both the x and the y direction. Now, if I have multiple forces acting on an object, which is a more general scenario, then I would say the total force, or the net force, which is the sum of all those forces, is equal to the object's mass times acceleration. If there are a lot of people pushing on a car, well, the mass of the car is pretty big, but you have a lot of people helping out, so that will make the car accelerate more compared to if you had just one person pushing on a car. And if you have a lot of people pushing on a shopping cart, well, a shopping cart is much lighter than a car. You have a really strong force and a relatively light mass. You're going to have a huge acceleration, as opposed to one person pushing on a shopping cart where you have a weaker force, but you still could get a reasonable amount of acceleration. Now, in the context, based on what we said here, we could refine our definition of what is mass from chapter 1. In chapter 1, we said mass could be thought of as the number of particles that make up the object, the number of nuclear particles, since protons and neutrons are much heavier than electrons. But here we could kind of think of mass as a resistance to acceleration. If an object has a small mass, it's really easy to make it accelerate, like a cart full of feathers. If a cart has a really large mass, like a cart full of gold, then it's incredibly difficult. You need a huge force before you can get that object to accelerate. So in this context, I could think of mass as an object's inherent resistance to acceleration. From the previous slide, we stated that if we know the force or forces acting on an object, we have enough information to determine the acceleration of that object, assuming we know the object's mass. In this course, mass will always be considered a constant, and mass will almost always be given in a problem. If you have multiple forces, you add those forces like vectors together, and then you say the vector sum of those forces, which I call F net, is equal to the mass of the object times the acceleration. Now, if you know what an object's acceleration is, then you have enough information to describe the object's motion. Basically, if you know AX and AY, and then you know some other initial conditions like initial velocity or initial position, you have enough information to find the object's velocity, position, and so on at a later time using ideas from 1D motion and 2D motion that we talked about in the 2 previous chapters. On the other hand, if you know how something is moving, if you know the positions and the velocities and the times, then that gives you enough information to calculate the acceleration. And if you know the acceleration of an object and you know the object's mass, then you can make some statements about the net force acting on the object. So we have this equation F net equals ma. Let's consider the scenario that we have already considered where there are 2 forces pushing on an object in opposite directions. And let's look at that idea in terms of this equation mathematically now. So if I have an object and I have a force pushing on that object in one direction, and I have another force that I call F2 pushing on that object in the opposite direction, well, this is a pictorial representation of adding vectors. What happens if I have one vector pointing up and to the right, I have another vector pointing down to the left? The vectors are equal in magnitude, but opposite in direction. Well, then the vectors cancel. And if the 2 force vectors cancel with each other, if the sum of these 2 vectors cancel, the left-hand side of this equation, F net, is just going to be 0. If F net is going to be 0, then what does that imply in terms of the object's motion? Well, if we said F net equals 0, I have 2 possibilities. Either the mass of the object is 0 or the acceleration of the object must be 0. Now, we are not going to consider objects with a mass of 0 in this course. We will always have some positive number for mass in PHY 121 and 122. So the only real possibility left for us is the acceleration of the object must be 0. Now, think about what we talked about in chapter 2. What does an acceleration of 0 imply? Well, if acceleration is 0, then that means velocity must be constant. The final velocity must be equal to the initial velocity. So if F net is equal to 0, if all the forces on the object add up as vectors to F net equals 0, that means the velocity will not change. Now, I want to take a moment to explicitly say, just because an object is moving does not necessarily mean F net is non-zero. If your initial velocity is 0 and the object is not accelerating, well, if initial velocity is 0 and acceleration is 0, that means the object will never accelerate. But on the other hand, what if the object is moving 5 meters per second to the west? If the object is initially moving 5 meters per second to the west and it is not accelerating, it will sometime later also be moving 5 meters per second to the west. So F net equals 0 does not mean the velocity is going to be 0. F net equals 0 means the velocity will not change. Whatever the velocity is now, the velocity will be the same thing at every time in the future as long as F net is equal to 0. We are now in a position to begin stating Newton's laws of motion. Newton's first law of motion is given in the textbook as every motion continues in its state of rest or of uniform velocity in a straight line as long as no net force acts on it. Basically, this is often stated as an object in motion will stay in motion and an object at rest will stay at rest unless an outside force acts on it. Now, when we say net force, as we said in some of the previous slides, net force means the vector sum of all the forces acting on a body. So if you have some object and there are a bunch of people pushing on that object all in different directions, you think of each of those individual pushes as a single force, and you add up all of those forces from all of those people as vectors. We said in chapter 3 that when you add vectors together, such as forces, you have to first break each of those forces from each individual person into its x and y component, and then you add all the x components from all the individual forces together, and you add all the y components from all the individual forces together, and that will give you the components of your net force in the x and y direction. As long as the net force is 0, we said on the previous slide, that implies the acceleration will be 0, and when acceleration is 0, velocity is going to be constant. So if velocity is constant, whatever type of motion you are in, you will stay in that same motion forever. One example of constant velocity is v equals 0, but there are other possible examples of constant velocity as well, such as v equals 4 meters per second in the negative x direction. So saying if something is at rest, it will stay at rest forever unless acted on by an outside force. This is just really a specific example of the general statement, when acceleration is 0, your velocity is going to be constant, just the specific case of v equals 0. But again, this is not the only possible example of F net being 0. Newton's second law is stated as F net equals ma. And this is what we argued in a lot of the previous slides for how to relate the total force on an object to the acceleration of that object. So one way you could kind of think of this is m is the mass of the object you are talking about. A is the acceleration or what that object is doing. Now notice at this point, both of these terms on the right-hand side of the equal sign are talking about the object. What is the mass of the object? That's a property of the object. What is the acceleration of the object? That is what the object is doing. On the left side of the equal sign, we have F net. F net is everything that is pushing or pulling on that object. So if the right side of the equal sign tells me about the object, the left side of this equal sign is telling me what is happening to the object from the outside. So you could kind of think of this equation as outside things that are affecting the object or doing things to the object are on the left side of the equal sign, and a description of a property of the object and what the object is doing are on the right side of this equal sign. As a first example to demonstrate this concept, let's ask, what is the force of gravity that attracts a 4-kilogram bowling ball towards the Earth, and what is the force of gravity that attracts a 10-kilogram bowling ball towards the Earth? Well, we learned in chapter 2 that no matter what your mass is, the acceleration due to gravity near the surface of the Earth is always going to be the same. Specifically, it's 9.8 meters per second squared downward. So what we're going to do is we will use Newton's second law, F equals ma, and we will apply it to the 4-kilogram bowling ball and to the 10-kilogram bowling ball. So the force of gravity in the y direction, I could write as the mass of the bowling ball, because the bowling ball is the object that we are talking about. And the acceleration of the bowling ball is going to be negative 9.8. Negative because the acceleration due to gravity is down towards the ground. The N here stands for newtons. Newton is the unit of force in the metric system. So if I send these numbers through a calculator, 4 times negative 9.8 gives me the force of gravity in the y direction is negative 39.2 newtons. For the 10-kilogram bowling ball, I could do the exact same thing. I have a mass of 10 kilograms over here. I have an acceleration of negative 9.8. And when I send that through a calculator, the force of gravity is negative 98 newtons. Now, you might ask, well, does it really make sense? Do I expect the Earth to pull harder on the more massive object compared to the less massive object? Well, how about we think of it this way? We want the acceleration due to gravity to always be the same. We want negative 9.8 to be our acceleration due to gravity in the y direction. If you think back to when we were talking about F equals ma, if I push on an object, that object will accelerate by some amount. If I want the same acceleration for a bigger object, I need to push harder, because if I push, I get some acceleration, but if I have a more massive object, I need to push harder to get that same acceleration. Here, we said we want the same acceleration in both cases. We want negative 9.8 meters per second squared to be our acceleration. So the force of gravity that the Earth pulls on the small bowling ball is going to be one number, but the force of gravity with which the Earth pulls on the larger bowling ball is going to be a larger number. I also want to point out that I use subscripts a lot here. In this chapter, we are going to often be considering both the x and the y direction. In principle, I could ask you something about the z direction, but like I said back in chapter 3, I don't feel I'm really adding anything by doing that, so I probably won't end up giving you anything in the z direction. And we're going to learn about different types of forces later on in this chapter, like we have the gravitational force, the tension force, friction, and so on. So I also like to have a subscript labeling what type of force I'm talking about. So here I have the gravitational force in the y direction. The last idea I'm going to propose in this video is when we look at an equation like this, on the left side of the equal sign, we have the sum of all the forces acting on an object. Force 1 plus force 2 plus force 3 and 4, and however other many forces we have on that object, all pushing or pulling in different directions. Often that is referred to as F net, so I write F net just as shorthand. And then we say the sum of all those forces is equal to the mass times the acceleration. Now, I did write all of these equations as vectors. So if you think back to vectors, vectors have both an x and a y component. Technically speaking, I can ask about a z component for the forces and the acceleration, but in my opinion, you're not really adding anything new to the problem. You're just making it more complicated. And I would rather ask something else. So it is very unlikely you'll see a force problem where you have to worry about the z direction. Now, because this force is written in this way as a vector, I could really look at this and say this is actually two equations where the sum of all the forces in the x direction is equal to F net in the x direction, and F net in the x direction is equal to mass times acceleration in the x direction. And the sum of all the forces in the y direction is equal to F net in the y direction, and F net in the y direction is equal to mass times acceleration in the y direction. So this one line written up here is really two equations where you have F net x equals max and F net y equals may. The reason I wanted to explicitly bring this up is if you are working through a problem, you set it up and you see that you have two unknowns, even though this is technically written with only one line on the slide, this is really two equations. One equation is F net x and the other equation is F net y. So if you have two unknowns in a problem, these could be your two equations that you work with. Now, again, I have to take every force individually, break it down into its components. I will write them all out on the sheet of paper next to me so they're right there and easy to see. But that is something that is going to be a fairly common recurring theme when we work through problems in this chapter. And you will see examples of us doing that when we do example problems on the board in a future video. So what did we learn in this video? We said the net force on an object is equal to the mass times the acceleration of that object. Net force is an idea that we're going to be seeing a lot, and net force just means the sum of all the forces pushing or pulling on an object. In some scenarios, you might have only one or two forces acting on an object. In other scenarios, you might have 1,000 forces acting on an object. You won't see that scenario in this course, by the way. But no matter how many forces you have acting on an object, the net force is the vector sum of all of those. So to find the net force, you would have to add all of those individual forces as vectors using the techniques we talked about for adding vectors in chapter 3. You would have to take each of those forces, individually break them down into their x and y components, add all the x components together to get the net force in the x direction, and add all the y components together of those individual forces to get the net force in the y direction. Now, when I say F net equals ma, as I wrote in this first line over here, I only wrote one line of an equation, but this is really three equations in one. I could say the net force in the x direction equals mass times the acceleration in the x direction. I could also say the net force in the y direction is the mass times the acceleration in the y direction. These two equations here are two different equations, and I should think of them as two different equations. One equation describes the forces and acceleration in the horizontal. The other equation describes the forces and the acceleration in the vertical. So if you are working through a problem, you have two unknowns, and you think to yourself, well, if I have two unknowns, I need two equations to solve it. F net equals ma is really two equations. It's just somewhat hidden because we have a vector arrow up here above F net and a, but this is really two equations in one. One equation for the x direction and a separate equation for the y direction. Now, if I want to be as general as possible, I could also think about the z direction, but as I argued before, I don't think you're really adding any new physics into a problem. You're just adding mathematical complexity, so you're not really gaining anything in terms of physics for doing this, and you won't see this very much, if at all, in this course. So the first statement above is really two equations hidden, and when it's written as one equation as up here. Sometimes you will hear F equals ma. I don't like to say this a lot because F equals ma is just a special case of this equation up here as well. If I have only one force, well then I don't have anything for F2, F3, and so on. So I just have my one force equals mass times acceleration. But I could generalize and account for every possible scenario by just saying F net equals ma. So I will almost never say F equals ma, even though you will see this a lot if you're looking at other resources to learn physics. And finally, I will say that in solving for the motion of an object, if you know F net, or if you are given enough information to find F net and you know the mass of an object, So you know the net force on that object and the object's mass. Then you have enough information to find the object's acceleration. And if the acceleration of the object is constant, which you will see here and there in this course, then you will be able to use ideas from Chapter 2 and Chapter 3 to determine aspects of the object's trajectory. How fast is it moving after some amount of time? How far has it traveled? And so on. So this is going to be the end of the first video. I'm going to have some example problems detailing solving force problems. And then after that, I will have a video dedicated to some specific forces that we're going to talk about, such as friction and gravity and tension.